In nuclear decay, after the completion of the concept of alpha decay, now we are going to deal with a very important problem of this chapter, and this is regarding the another decay process which is called beta decay. So this is the first lecture on beta decay. So I will just give you a brief introduction regarding this beta decay process. And this chapter is equally important for the students preparing for various competitive examinations like the civil services examination as physics as an optional subject, and also for the students preparing for NET and JRF examinations and various academic examinations like the course on BSc or MSc or engineering sciences. So be serious and attend all the lectures on this topic. Definitely you will be benefited. In fact, a stable nucleus has a proper ratio of the number of neutron and proton. You have definitely studied that in case of a stable nucleus, the ratio of the number of neutron n and the number of proton z, this is almost less than 1.5. So when the ratio of number of neutron and number of proton is less than 1.5, then generally you say that the nucleus is stable. But imagine if this ratio gets altered, that is, the ratio of n and z is not less than 1.5. In fact, in that condition, the nucleus becomes somewhat unstable. And you can think how this instability will be raised. The instability means the ratio of n over z will be altered from this proper value which is required for the stable nucleus. This will be actually led by two regions. First of all, you can see that if the number of neutron n over one proton, that is n over z, which is required for the stability, is more than the number of neutron present in the nucleus. It means if let us consider for example that for each 10 proton, it means z equal to 10, there are 14 neutron. It means when there are 14 neutrons and 10 protons, then the nucleus is stable. Let us consider. But if the number of neutron becomes, let us consider 16, but the number of proton remains 10, then this ratio is altered from the previous value which was actually required for the stable nucleus. In that condition, your nucleus will become somewhat unstable. So in this condition, we say that the instability has been developed due to the excess of neutron. So the instability in the nucleus due to the number of neutron and number of protons will be caused by two regions. The first one is excess number of neutron over the number of required required for stability. It means the number of neutron is more than the number which is required for stability. As for example, as I have told you that if for stability the 14 neutron is required over the 10 proton, but if there is a number of neutron greater than 14, then the nucleus will become somewhat unstable. And this instability is caused due to the excess of neutron. On the other hand, let us see if in this example if the number of proton now becomes, let us say, 12, but the number of neutron remains 14, even then the ratio of n and z will alter, and the cause of this instability will be actually the excess number of proton. Here excess number of proton does not mean that the number of proton is greater than number of neutron. It is although less, but only 10 proton was needed for stability, but now there is 12 proton, so the nucleus will become unstable. So this instability is caused due to the excess number of proton. So I have mentioned it here that due to excess number of proton over the number required for stability. So there are two regions for the instability, and due to those two regions the ratio n over z gets altered and the nucleus becomes unstable. So in fact such unstable nucleus tends towards stability, and to get the stable state, what the nucleus will have to do, you can think. So you can think, if the cause of instability is excess number of neutron, then definitely the nucleus will have a tendency to decrease the number of neutron, because the excess number of neutron is the cause of instability. So stability will be fixed only when the number of neutron will be decreased. So if the cause of instability is excess number of neutrons, such a nucleus tends to convert a neutron into proton. So when a neutron will be converted into proton, in first hand the number of neutron will be decreased, and on the other hand number of proton will increase, and so the ratio n over z will be such that the nucleus will become stable. Okay. But if the cause of the instability is excess number of proton, then such nucleus will convert a proton into neutron. A proton into neutron, because the cause is excess number of protons. So nucleus will tend to decrease the number of proton, and on the other hand it will also increase the number of neutron, so that the ratio n over z will be maintained for stability. So in this former case, where instability is caused due to excess number of neutron, in those nuclei the nucleus will suffer a transformation of neutron into proton, and if the instability is due to the excess number of proton, then the nucleus will suffer a transformation where proton will be transformed into neutron. Actually, in these two processes, when neutron will be converted into proton and proton will be converted into neutron, then you will see that a particle will be emitted, and that particle is called beta particle. In fact, this beta particle will be of two types, that is negatively charged beta particle and the positively charged beta particle. You can see this thing here. Actually, now let us consider this process. This n is converted into proton, and at the same time an electron has been emitted. You can see this electron is nothing. This is called beta minus. Electron and beta minus are same thing, and this process you may call minus beta decay. Okay, although this is not an actual process, because in this lecture we are going to see how this process will be not possible, although at present I have considered that a neutron has been just converted into a proton and an electron, that is beta negative, and on the other hand a proton is converted into a neutron and a positron. This E plus is what? This is positron, which is actually the antiparticle of electron. Positron means antiparticle of electron, and this is called beta plus particle, or you may call this process beta plus decay. As I have told you, this is not the actual process. What will be the actual process? We will deal with that fact after some time. But definitely a question in your mind has been arised that how this neutron is converted into proton. Actually, inside this neutron or this proton, a weak force acts, and that weak force operating inside the neutron and proton is responsible for its conversion into a proton and a neutron. So I have mentioned it here that these transformations take place because of a weak forces operating within a neutron or a proton. Okay. But as I have told you that I have just considered that a neutron is converted into a proton and an electron, that is beta minus, and a proton is converted into a neutron and positron, and that positron is called beta plus. But is the actual state of affairs like this? In fact, you know, in any nuclear process, the principle of conservation of different type of conservation principles must be satisfied. Whenever any nuclear process or any nuclear reaction takes place, all the conservation principle must be valid, and if all the conservation principles are valid, only then you can say that process will proceed. So we will test that these processes of conversion of neutron into proton into an electron, or a proton into a neutron and a positron, these are valid processes or not. We will check on the basis of the different conservation principles. Okay, you can see that actually the one of the principle of conservation of charge is valid here. You know, neutron has no charge, but this proton has +1 charge. Okay, and electron has -1 charge. So the initial charge is 0 and final charge is also +1 and -1, that is 0. So in accordance with the charge conservation principle, this reaction will take place. It means the charge conservation principle is valid here. Similarly, in the second reaction, you can see the proton has +1 charge, neutron has 0 charge, and positron has +1 charge. So this reaction is also valid on the basis of principle of charge conservation. But apart from this principle of conservation of charge, you will see here that actually the three basic conservation principles, those are actually the energy conservation, linear momentum conservation, and the angular momentum conservation principles, are not actually valid in these processes. You will see there will be an apparent violation of these three principles if the process will take place like this. That is, if you say that a neutron will convert into a proton and an electron, then you will see that neither the principle of conservation of energy nor the principle of linear momentum and the principle of conservation of angular momentum will hold in this process. So definitely there is some lacking here. Something is lacking here, because if this process is correct, if this process will take place and if it will be experienced in observation, then all the conservation principles must be valid. So we say that these processes of beta decay have puzzling aspects. And what are those puzzling aspects? As I have told you earlier, that there is an apparent violation of conservation principles of energy, linear momentum, and angular momentum. Actually, these conservation principles are violated if the process will take place like that. So definitely the actual process will be not same as that I have mentioned earlier. So now let us consider a beta minus decay process. We consider a parent nucleus, let us say X, whose atomic number is Z and mass number is A. And when it suffers the electron emission or beta minus decay, then you can see the daughter nucleus will have a atomic number Z plus 1 and mass number remains same. Why? You can understand it. Because here electron emission takes place, so definitely there is a conversion of neutron into proton and electron. So you can see, since the number of proton is increased by 1, on the other hand the number of neutron is decreased by 1, so the total number of nucleons remains same. Number of nucleons does not get altered, because number of nucleon means number of neutron plus number of proton. So as the number of neutron is decreased by 1 but the number of proton is increased by 1, so the total increase or decrease in number of nucleon remains 0. So mass number remains same. But as one proton has been created from the one neutron, so number of protons has been increased by 1, and therefore the daughter nucleus has a atomic number of Z plus 1, because atomic number represents the number of proton. Okay, I have considered this process. This again, I am telling you that this is not the actual process, this is not the correct process, but our aim is to deal with why this process is not correct, why this is incomplete. This is our aim. So to deal with this fact that this process will take place or not, let us calculate the Q value of this process first of all. And you know, for calculating the Q value of any process, we first of all find the rest mass energy of the reactants or the initial constituents, and again the rest mass energy of the final constituents, and the difference of these two gives actually the Q value. So you can see what will be the rest mass energy of the initial constituents. Initial constituents rest mass energy, I have assumed it Ui. In fact, this Ui will be what? This is m of Zxa minus Zme. What is this m of Zxa? Actually, Zxa, this is nucleus, but this mass of Zxa is not the mass of the nucleus. It is mass of the atom of this nucleus. The atom whose nucleus is Zxa, this mass represents the mass of that very atom. But you know, in atom there is nucleus and plus electron, nucleus plus electron, but you have to write the mass of the nucleus. So when we will subtract the mass of the electron from the mass of the atom, then we will get the mass of the nucleus. So this m into Zxa minus Zme. Why minus Zme? Because this atom has Z proton, so this will also have Z electron, and Me is the mass of one electron, so total mass of Z electron will be Zme. So when you will subtract the mass of these two electrons from the mass of atom, then you will get actually the mass of nucleus. So this quantity inside this square bracket, this is mass of nucleus, mass of nucleus, okay, and multiplied by C square. So this is the rest mass energy of the parent nucleus, you can say. Now we have to find the rest mass energy of the final constituents. Again, see here in the product, this Y is the daughter nucleus, not the atom. But in our calculation, we will write the mass of the atom. So UF will be what? This is m of z plus 1 ya minus z plus 1 me up plus me. What is this? You can see this m actually represents the mass of the daughter atom, not nucleus. This m is the mass of daughter atom, and when you will subtract the mass of the total electron in the daughter atom, then you will get the mass of the daughter nucleus. So m into z plus 1 ya minus z plus 1 me, this is actually the mass of the daughter nucleus. This is mass of the daughter nucleus. And as one electron is also emitted, so I have added here the mass of that electron. And then you multiply it by c square. So this is your rest mass energy of the final constituents. And you know the kinetic energy will be what? If you want to find the Q value of this process, what will be equal to the Q value of this process? So I have not mentioned it here, but you can see that this Q will be equal to what? This will be Ui minus Uf. Ui minus Uf. And when you will subtract this Ui minus Uf, you can see here this Me will be cancelled by this minus Me, and there will be minus Zme here, and in the expression of Ui there is minus Zme. So when you will subtract, this mass of the electron will cancel out, and Ui minus Uf will be simply equal to m of Zxa minus m of z plus 1, sorry, this is z plus 1, not z. This will be z plus 1 ya times c square. This is actually the Q value of this process. Okay, you know the Q value of the process is shared by the shared as kinetic energy by the products, and here in the product there is a daughter nucleus and an electron. As the daughter nucleus is so heavy that we can think that the kinetic energy shared by the daughter nucleus is almost negligible, almost zero. So you can assume that the total Q value appears as the kinetic energy of the emitted electron. So what will be the kinetic energy of the emitted electron? That will be simply equal to Q. So kinetic energy of emitted electron will be equal to Q. It means the kinetic energy of the emitted electron will have a definite value. It means if the process of this beta emission or electron emission will take place like this, that is, a parent nucleus will convert into a daughter nucleus emitting an electron. If the process takes place like this, then definitely the emitted electron must have a definite value, a constant value of kinetic energy, and that kinetic energy must be equal to, almost equal to, the Q value of the process. But is the experimental result same as we are talking about? The fact which we have just told, are the experimental result like that? Definitely not. So I have mentioned it here. What is observed in the actual experiment? We have calculated that the kinetic energy of electron will have a definite value. When it will have a definite value? when the process will be just as I have shown, that a neutron will be converted into a proton and an electron, then the kinetic energy of the electron should be constant. But you will be surprised that in actual observation, in actual experiment, the kinetic energy of the beta particle or the electron is not constant. When experiment is performed to observe or to measure the kinetic energy of this beta particle or electron, it is found in the experiment that the kinetic energy of the electron is not constant, but it varies continuously from 0 to a maximum value, a k max. And this k max is different for different nuclei. You can see this graphical plot. In fact, this is relative number of electron which will be emitted by different nuclides, and here I have written on x-axis the energy of the electron. You can see this graph. This graph shows that the total energy of the electron will be 0 here. Here actually the energy value is 0, and here the energy is actually maximum. It is maximum. So the energy of electron actually varies continuously from a 0 to a maximum value. Here actually this cuts this energy line, and so this represents actually the maximum value of energy of electron. But if the neutron will be converted into a proton and an electron, then you have seen that the energy of electron should be constant. It should not vary. But actual experiment says that the energy of electron is not constant, but it varies from 0 to a maximum value. In fact, the maximum energy of this electron can be given as like this. This is m naught c square plus k max, which is just equal to, almost equal to q. In fact, q means, don't write q, because q is actually the value of k max, you can say. And here total energy means the maximum kinetic energy of the electron and the rest mass energy of the electron. But this rest mass energy is constant. So this variation, you can also say that this is the variation of kinetic energy, because m naught c square is constant. So what is seen in the experiment? Theoretically, when you say that the process will be conversion of neutron into proton and electron and no other particle is emitted, then theoretically we say that the electron's energy should be constant, but the actual experiment says that the energy of electron is not constant, but it varies continuously from 0 to a maximum value. So this experimental observation does not support this process. It means definitely there something is lacking here. In this neutron will be converted into a proton and electron. This is not correct. Definitely some other particle should be emitted. Okay. So this was the first experimental observation, which actually indicates that the process of conversion of neutron into proton and only electron is not the correct process. Now let us see the conservation of linear momentum. As you can see that this is your parent nucleus, and this is your daughter nucleus, and this is your emitted electron. Now the parent nucleus is assumed to be at rest, and when the this decay process will take place, then the daughter nucleus will recoil. This is the daughter nucleus Y, and this electron will move with some velocity. This is your electron. So according to the principle of conservation of linear momentum, if the linear momentum remains conserved, then the initial linear momentum must be equal to the final linear momentum. Initial means before this decay process, the total linear momentum of the system, and after decay, the total linear momentum of the system. So Pi must be equal to Pf. But as we have assumed that our parent nucleus is at rest, so Pi will be equal to 0. Okay? But what will be Pf? Pf means the total linear momentum of the products. And in products, products have actually two components. First one is the daughter nucleus, another is the electron. So Pf means momentum of the daughter nucleus Y and the momentum of the electron. So 0 is equal to Py plus Pe, and therefore you can say that Py must be equal to minus Pe. So if the linear momentum will remain conserved in this process, then definitely the linear momentum of the recoiling nucleus, daughter nucleus, must be exactly equal and opposite to the linear momentum of the electron. Only then you can say that linear momentum remains conserved. But what happens? What actually happens? What you see in the observation? In fact, in observation, it is seen that this Py is not exactly in opposite direction of Pe. This is our experimental observation. So I have mentioned it here. You can see that when the directions of the emitted electrons of the and of the recoiling nuclei are observed, they are almost never exactly opposite as required for the linear momentum to be conserved. Okay. So experimental observation is against of this. In experiment, it is seen that actually Py and Pe are not in just opposite direction. So definitely the linear momentum conservation principle also does not hold when you consider that a parent nucleus will convert into a daughter nucleus and only one electron will be emitted. So this process cannot take place. This is not a valid process because conservation of linear momentum is not valid in this process. Okay? Now we will see the principle of conservation of angular momentum will be valid in this process or not. You will see that actually the principle of conservation of angular momentum is also not valid if the process will take place like this. Why? You know, the neutron, the proton and the electron, all these three particles are fermions. You know it. And as neutron, proton and electron are fermions, so all are half spin particle. Every particle has a spin half. Okay? And if beta decay involves just a neutron becoming a proton and an electron, a spin, and hence the angular momentum is not conserved. How you can say? You can see if you consider that a neutron is converted into a proton and an electron. Okay? Now let us see that the spin of this neutron is 1 over 2 h bar. This is a spin angular momentum in fact. And if you consider that this proton and this electron are in fact of up spin, then this total momentum, angular momentum will be 1 by 2 h bar plus 1 by 2 h bar. So the angular momentum of the reactant is 1 by 2 h bar and the angular momentum of the product is actually h bar. So you can see that the angular momentum of neutron is not equal to the sum of the angular momentum of the proton and electron. On the other hand, if you assume that this proton and electron are actually in fact the unlike a spin state, that is the proton has a spin up and the electron has a spin down, then what will happen? Then the spin of neutron will be 1 by 2 h bar, and that of the product will be 1 by 2 h bar and minus 1 by 2 h bar. And that will be equal to 0. This is equal to 0. So you can say that the spin angular momentum of the neutron is not equal to the spin angular momentum, or simply you can say the angular momentum of the neutron is not equal to the angular momentum of the proton plus electron. So you can say that the angular momentum is also not conserved in this process. So what we have seen, you have seen that actually neither the principle of conservation of energy nor the principle of conservation of linear momentum and angular momentum are valid or get satisfied when we consider that a neutron is just converted into a proton and an electron. So that process of decay is not a actual process, that is not a correct process. So this was just a puzzle. This was just a puzzle in physics, and this puzzle was actually resolved in 1930 by Pauli. Actually, Pauli proposed that in this process, an uncharged particle whose rest mass is 0 and spin is equal to half is also emitted along with the electron, and that particle later on called neutrino by a great physicist Fermi. This name neutrino was given by Fermi, and this is actually called the Fermi hypothesis, and we will discuss later on Fermi's theory of beta decay in very detail. So how this problem was solved? What will be the actual beta decay process? That was solved in terms of the neutrino hypothesis. What is this neutrino? As I have told you, that neutrino is a massless particle. Its rest mass is assumed to be 0, and its spin is also half. This is also a fermion. So when we consider that along with the electron a neutrino is also emitted in this process, then you will see that all these conservation principles will be valid. And so after this neutrino hypothesis, the actual beta decay process was came into existence, which is now valid. So you can see that in this process we consider that the neutrino carries energy equal to Ke max minus Ke of the electron. It means the neutrino also carries energy. And what will be the energy carried by the neutrino? The energy carried by the neutrino will be equal to the maximum kinetic energy minus Ke. Maximum kinetic energy means Q value. Q value minus kinetic energy of this Ke means kinetic energy of electron. And the remaining energy actually appears as the kinetic energy of neutrino. Kinetic energy of neutrino. Sorry, this is just neutrino. Kinetic energy of neutrino. Okay. Now, this neutrino actually balances the linear momentum too. As you have seen that in case of the electron emission only, the total linear momentum of daughter nucleus and the total linear momentum of the electron was not balanced. But when we consider that neutrino has also linear momentum, then actually it is seen that the linear momentum of the daughter nucleus, this will be equal to minus linear momentum of the electron and plus linear momentum of the neutrino. then angular momentum remains conserved. Okay. Now, neutrino is a spin half particle. Now see, if in this process we consider that neutrino or antineutrino is emitted, see here the actual process. When neutron is converted into proton, then along with this electron, antineutrino is emitted. This new bar is antineutrino. And when proton is converted into neutron, then along with this positron, that is beta plus, neutrino is emitted. Okay, and both a neutrino and antineutrino has a spin half. So now you can see that how the principle of conservation of angular momentum holds now. You can see, let us consider this process. The spin of this neutron will be 1 by 2 h bar. Okay. Now see, a spin of proton, if you consider this is a spin up, this will be 1 by 2 h bar. And if you consider that this electron is a spin up, this will be 1 by 2 h bar. Definitely, if the electron will be in up spin state, definitely this antineutrino will be in down spin state, and so this will be minus 1 by 2 h bar. Now this will cancel out, and you can see that the angular momentum of the reactant and the product are same. Similarly, you can also think that if the proton is in up spin state, so its angular momentum is 1 by 2 h bar. Electron is in down spin state, then this will be minus half h bar. And if electron will be in down spin state, definitely the antineutrino will be in up spin state. So this will be 1 by 2 h bar, and so this will cancel out. And so again you can see that this half h bar and this half h bar are equal. So after considering that in this process, along with the electron, neutrino is also emitted, then all the conservation principles become valid. And so actual beta decay process, a neutron is converted into a proton and an electron and antineutrino. And similarly, in beta plus decay, a proton is converted into neutron, positron and neutrino. Okay. So I have mentioned it here that the two kinds of neutrinos are involved in beta decay, the neutrino itself and the antineutrino. So this was just a brief introduction regarding the beta decay, why neutrino hypothesis is needed for the beta decay process. I think you have understand. Now in the forthcoming lecture we will see the more advanced concept of this beta decay process.